We present Gen H2R, learning generalizable human-to-robot handover via scalable simulation, demonstration, and imitation. In our work, we explore one of the human-to-robot interaction tasks, human-to-robot handover, hoping robots to reliably receive moving objects of diverse geometry from humans, based on egocentric visual observations. There are several challenges for this task. Firstly, training a robot in real-world scenarios entails increased risks and expenses. Secondly, creating a substantial number of assets for H2R handover is also a complex task. Thirdly, collecting robot demonstrations receiving objects from real humans is very costly and unscalable. Faced these challenges, we propose a novel framework to scale up the learning of human-to-robot handover, which consists of a simulation environment named Gen H2R Sim with large-scale benchmarks, an automatic robot demonstration generation pipeline for vision-based closed-loop control, and a forecast-aided 4D imitation learning method effective in distilling large-scale demonstrations. To diversify geometry and motion assets depicting humans handing over objects, we introduce a new environment, Gen H2R Sim. We use over 3,000 different objects from ShapeNet and use DEX GraspNet to generate hundreds of grasp poses for each object. We procedurally leverage animation curves like Bezier curves to mimic hand-object moving trajectories. Given the challenges in scaling up real-world mocap datasets, we opt for a large-scale synthetic dataset. Combining various grasping poses and moving trajectories, we generate about 1 million complex synthetic H2R handover scenes. Based on Gen H2R Sim, our main focus is to introduce a distillation-friendly demonstration generation method. To generate expert demonstrations in the dynamic handover setting, one policy is a four-sided planner. It plans once based on the privileged destination, which is smooth but does not align actions with the dynamic visual observations. Another policy is a short-sided planner, which replan frequently, and may generate unsmooth trajectories. In contrast, our landmark-based expert planner periodically replans based on the privileged hand and object states in the future. When encountering an endpoint, it shouldn't foresee the actual object future state. The hand and object keep moving and the planner continues to replan periodically. And when the object moves to its destination, the planner grasps the object correspondingly. Compare with naive methods, we observe that our method excels in generating smooth expert actions while ensuring a robust vision-action correlation, making it distillation-friendly. In this way, we automatically generate 1 million high-quality expert demonstrations suitable for learning, which scale up the high-quality dataset for our forecast-aided 4D imitation learning. Our policy inputs an egocentric object hand point cloud. For each input point, we compute its past coordinates using flow information obtained through the iterative closest point algorithm. Subsequently, we employ PointNet++ to encode the processed point cloud into a low-dimensional global feature. Then the policy head decodes this feature into a 6D egocentric action, serving as the primary policy output. Simultaneously, the prediction head decodes the feature into future pose transformations, contributing to the auxiliary loss. We compare our method with baselines. Quantitatively, our model outperforms state-of-the-art method Handover Sim 2 real by a large margin in all benchmarks, demonstrating that scaling up efforts result in substantial improvement of generalizability to novel geometry and motion. Qualitatively, in the benchmark proposed by the previous handover simulator Handover Sim, our method can find better grasps and avoid frequent pose adjustments when the gripper is close to the object. In our proposed large-scale benchmark, our model can predict the future pose of the object to enable more reasonable approaching trajectories, and can generalize to unseen real-world objects with diverse geometries. We also deploy these models on a real robotic platform. For more complex trajectories including rotations, our model demonstrates robustness compared to baseline methods. For novel objects with complex trajectories, our model exhibits greater generalizability. In conclusion, to learn generalizable H2R handover, we propose a simulation environment named Gen H2R Sim with millions of handover animations, an automatic robot demonstration generation pipeline for vision-based control, and a forecast-aided 4D imitation learning method. And we make sim-to-real transfer for the framework.